Thank you very much for the introduction. I hope you can see my slides, myself, and here. And if anything goes haywire during the next few minutes, please just let me know. Great. So yeah, as was mentioned, my name is Raphael Sznitman. I'm a professor at the University of Bern, where I lead a group in machine learning and computer vision for medical applications and imaging. Both on the side of diagnostics, but also on interventions. And so today, what I'm going to be talking about is a little bit about what we've been doing over the last almost decade when it comes to finding instruments in computer vision, from a computer vision point of view, but finding instruments in surgery or looking at video feeds of surgery. And there's been, as you'll see, a tremendous amount of progress that has been done, which is great. And now we're coming at a point where we start having to really look a little bit inside and say, well, what's the last step that we need to go further? And so that's what I'll spend the last part of today's talk looking at. How do we get over those last few cases that still are problematic? So just to get going, what I'm really talking about when I mean finding instruments in surgery is something like this. So this is a video feed from a Da Vinci surgical instrument scene. So this is the Da Vinci robot. You can see different instruments that are being manipulated by a robotic system where it's a console with a physician operating it next to it and the robot sitting over the patient with the instruments inside the gastric cavity. And so here you can see different instruments are being used. The frame rate here is at about 1 frame per second, so a little bit reduced, but in reality it's around 60 frames per second. You see tool interactions, you see an anatomy which is highly complex, deformable, with shadows. Typically you can have blood, you have change of scenes, scales, focus, and so on. So really a rich environment of things happening. And so over the last, I'd say, decade, there's been a trend to provide computer vision methods that can look at these video sequences and analyze them, either post hoc, so meaning you have the whole sequence and now you want to say something about the content. What were the different things that went on during the surgery? Were there problems? Or in a live mode, so in the sense in a real-time perspective, what is happening to the instruments, and potentially can you provide some safety measures for a robotic system that is using this information? So are you coming close to a structure inside the body that you should pay particular attention to, and so on? So you might wonder, well, if you have a robotic system, why do you care, right? Why do you care about looking at imaging? So that's a very normal question. And so this is actually a visualization provided by Austin Ryder, who used to be at Columbia, highlighting what is the difference between what the robotic system, so the actuators of the robot, when you overlay them on the imaging. And that's this yellow line, right? And yet you see the instrument is actually somewhere else. And that's to highlight the fact that just using the information from the robotic system to know where the instruments are is often actually really a bad idea, because those aren't precise to the extent that you need them to do anything meaningful within the surgery. So that's why computer vision methods for analyzing video content have really gathered quite an interest in the last few years, and now they're a regular international challenge for detection and segmentation of instruments in this surgical environment. So what we've seen over the last bit, as I mentioned, is sheer progress, and that's fantastic. This is just an example coming not from gastric surgery, but this time from eye surgery. This is a surgical instrument. That's the retina behind. And here again, you want to be able to detect these instruments during the procedures. Now, on the right, I'm showing you performances, and forget the actual methods. That's not important. The actually interesting part is looking at the progress that we've seen. And so over the years, from green, blue, magenta, and now red, what you see is over time is an interesting progress in the development of these methods. They're becoming more and more accurate in their ability to track more and more precisely. So this is threshold error. So pixel-wise threshold errors versus accuracy. And this has been on one side because the methods have gotten better and better, but also on the flip side because there's been more and more data to train them. And that's why these challenges are more and more attended in the recent past. So, but why is it hard? Why is it hard? And so broadly put, the problem comes down to generalization. While it might seem that in surgery, you're basically in a very enclosed environment, things are very controlled, which is true, the reality is that a lot of things can happen and will happen during surgery. So that can go from dealing with blur, simple things like image blur that will happen naturally during the procedures, to shadows, to how do you distinguish the instrument from a shadow, occlusions from the anatomy, discontinuities from the instrument because of the anatomy, smoke and blood that might appear. So there's a wide range of things that are going on in these video sequences. And so being able to have very resilient and very robust methods that are able to detect these instruments has been and remains to some extent a challenge. And that's what I'm going to be talking about now, is just some methods that we've developed in the group to kind of move us forward along this path. And then I'll show, well, what's really remaining anymore at this point in time, and what are we looking into to achieving the next step. So I'm going to start with something that makes sense into trying to estimate pose of instruments. So when I mean pose estimation, I'm really talking about being able to identify where a surgical instrument is in a field of view. So what we can typically say when we have an image like this is this whole scene actually can be you can break it down into a scene might have multiple instruments that you want to detect. So you have that's already to take into account. And at the same time, an instrument has multiple parts to it. So it has a shaft, it has a wrist, it has tips, it has tweezers. These things can open and close like scissors. So you have these multiple parts that are important in order to understand where they are, both in terms of robotics, but also in terms of what is the general thing that's happening during surgery. What is actually going on? So in the first step, one of the things some years ago that we thought was, well, let's try to have some kind of scene model to understand this entire scene when it comes down to the instrument. Now, when I mean a scene model, I'm really just talking about the instruments themselves, not the much more complex geometry that's happening behind. So you can take a probabilistic point of view, like what we saw earlier, Eric's talk before the break. And really what we were interested in doing is having a mathematical approach to detecting multiple instruments. And these multiple instruments have different parts. So you have the different tools, but you also have, for every tool, the different parts that are in this place. And you want to somehow learn this joint distribution, which is highly, highly complex. So one simple way to break this down is to assume that you have a much simpler distribution, which at the time we assumed a fully an independence between the instruments themselves, but also a conditional independence between the joints or the parts given the instrument itself. And so you have a very, very simple representation now of a complex scene. So once you have this kind of scene model, you can start to model. And that's what we started looking at. So this first part is really about a binary representation of whether or not the instrument is there. And that's basically saying image classification, or is this image containing an instrument of type A or B? And on the other side, this conditional distribution that we have of the joints given the instruments, well, this can also be modeled in a likelihood model. So in particular, you can say, well, if my instrument is there, or it's not there rather, in this case, well, you're just going to assume that it's a uniform distribution. And on the flip side, if it's actually present, we're just going to have a 2D representation that's representing this image and a point, right? So a point is representing where now a joint is located on an image. So it's a key point representation. The nice thing about a model like this is you can actually optimize it very well using the binary cross entropy, which breaks down these components very nicely, because these Bayesian factors can actually be very nicely propagated through an entropic function. So what we basically have is a very simple network approach, which on the first part, if you want to estimate the likelihood of the priors, if you want, of whether or not an instrument is there, can just boil down to a standard architecture network that is trying to do classification, whether or not an instrument or another is present. And in order to basically estimate the rest of your distribution, you can actually use a unit-like structure to estimate the joint distributions of the joints given in models. So a very simple approach with a simple function to optimize it. So in practice, when you do this, you can actually have some decent results, being able to do multiple instrument tracking with these different joints. What I'm showing on the left in green are the ground truth points, and in colored are the overlaid estimates of the model. And on the right here is just the numbers actually showing this. In this case, it's automatically detecting whether or not there's one or multiple instruments. That's what that first term was looking to optimize for. And in the second, it's actually all these numbers provided here. So in general, this was providing a very interesting approach, but it has its limitations, being that all you're doing is estimating these key points, which often are very ill-defined, and for every instrument, those change, in fact. So that's why a lot of the community, not just us, but a lot of the community started thinking about segmentation in a much broader way, or even beyond that, going from instruments, or from pixels rather, to instrument segmentations and instances as a whole. So the so-called instant classification problem. So in our setting, what's a little bit unique is that we have these surgical instruments like this. And if you're talking about segmentation, well, it's important to specify what kind of segmentation are we talking about. So on one side, you can say, I'm going to segment the parts, so perhaps the shaft of the instrument. And so for this one image here, you can see that you can classify a shaft for two different instruments in the same way, right? This is the same type of structure or part of an instrument, a shaft. And then the neck is a different part, right? But yet at the same time, if you think about it more globally, then really you have two different instrument types that are here. And this highlights the first problem to realize when we talk about detecting instances in these cases, is that for many instruments, actually, their parts look the same, but only very specific parts within those instruments allow you to say something about the type of instrument they are. So what distinguishes these two instruments isn't the shaft, it's this tiny bit at the very end, right? And that's what allows you to ultimately be able to make this judgment. So context, as you can imagine, plays a critical role in being able to make proper decisions on these kinds of cases. So this is something that we've witnessed also over the last few years with challenges, international challenges, both at MICAI and others, is that when we think about binary segmentation, part segmentation, and instrument segmentation, really it's a difficulty going from top to bottom. And so here what I'm showing was an extract of a paper in the community looking at basically the ground truth for these different cases for this one image and how different methods were performing. And so what you can see is that binary segmentation in general does very, very well. When we consider parts, it does pretty well as well. In this case, the results are pretty good, but it's not perfect. So since you have some errors that are propagating, and for instance, here we're missing potentially some parts. And then for the instruments, it's often very confusing. It doesn't really know because the context is what's allowing you to make a decision. So here you can really see that on instrument segmentation itself, the results are quite poor. And so that's what we started focusing on. How can we approach this last part a little bit more effectively? So in particular, we need to overcome a few things. First, that different instruments, as I mentioned, have similar parts to them, and they appear the same way. Some instruments can occupy huge proportions of the image, depending on what the surgeon is doing, and others can be very small. And then also instruments can overlap and form discontinuities. And that makes it really hard in order to say what pixel belongs to one instrument and so on, right? So if two instruments are crossing, it makes that distinction really hard. So many approaches that have tried to go in this way have really tried to first have a method that finds a bounding box around your instrument, and from this do the segmentation. And so that helps with some of these things, but often one of the issues is that you include, as in this case here, you include information from multiple instruments. And that's where all the errors then come through, because they assume that there's only one instrument in these boxes. And so it doesn't really know how to handle this overlap, right? And so this is where we figured, well, hold on. Instead of using these bounding boxes to do this, what we wanted to do is leverage the instances and the parts at the same time. And so this is what I'll briefly show. This is recent work that was of this year, where we're going to approach it using a network architecture that on one side is going to do very effective mask or part segmentation. As I showed before, we know from the community how to do this pretty well. This is basically doing segmentation with losses that are very standard. This works out well. But then what we're also going to do is try to estimate two other quantities that are related and help actually with the optimization process. And that's the offset estimation. So meaning for every pixel in an image, we want to know how far in Euclidean distance it is from the centroid of the instrument it actually belongs to. So if you're part of an instrument, we want to know how far that pixel belongs to. And then at the same time, we want to estimate the center of the instrument. Okay, so these two quantities, therefore, are codependent on each other, but they're estimated for the moment separately. From this, we can then start to think about how to bring these quantities together. So on one side, we can take this and use it as a mask to combine it with the offset. So this is basically just a dot product allowing for a masking effect. And then combine this with the centroid approach that we have here. And so what you end up having then are piecewise constant instances for a given instrument that uses this mask offset and the centroid to determine who belongs to who. And from this, you can optimize this and then classify each of the instruments or instances that you have into a traditional image classification problem for every instrument part or instance at that point. And when you do that, this is what you get. Basically, this is a video from a challenge data set that was from last year. What you can see is that now we're able to more or less detect the instruments, segment them fairly well. And even in cases where you have some overlap, that's what's happening here, you're able to do something that is fairly reasonable in terms of instance segmentation and classification of these instruments. So we were quite happy with this results and looking very, very positive about the ability to move this forward in practice, of course. But as always, it's really important to understand where your models are making mistakes. So we took a deep dive about a year ago into understanding this. And so we still saw mistakes like this. So here it's a completely blurry image. So most of the cases are correctly predicted, but actually one of them is very far off. And then we had cases like this, where actually we are losing a quarter of the image because of some processing that had happened on the console system. And this is exactly where we stand in a way, where we have lots of cases that are working great. And now if you want to have this running in a critical system, these less than 1% mistakes that we get are due to a variety of facts. And that's what I'd like to talk a little bit about now, is some recent work and direction that we're looking into. It's really about the fact that neural networks are fantastic, but fundamentally they are unaware of what they don't know. And what do I mean by that? So I'm going to switch context out of surgery and into diagnostics. In this case, it's in the context of OCT imaging, so optical coherence tomography. So this is eye care mainly. This is an image of a cross-section of an eye scan. And here what you see are parts of the retina. And in fact, what I'm going to be talking about is unrelated to the anatomy. It's unrelated to the application itself. I'm just showing you a generic problem, in fact. So this will translate to MRI, to CT, and so on and so forth. So what happens often is that you take an image, you pass it through your neural network, and you're hoping to get some binary classification. Is this case pathological or healthy? In this case, the model says it's pathological, and you're happy because that's actually true. In this case, you have a healthy case, you push it through your network, and it says you're healthy, and that's great. But the question is what happens in this case where you now push an image that is corrupted. So half of the left side somehow has disappeared. This is coming from the actual machine itself. And you push it through the system, and it's, again, going to give you an answer. And this is where the danger comes in, because you've predicted something when you really shouldn't have, right? And so we actually applied this on a very large cohort of about 100,000 OCT scans that corresponded to about 50,000 patients that are in our eye clinic here in Bern. And we started seeing mistakes of this kind. So in this case, this turned out to be a real mistake. Our system shouldn't evaluate it. Why? Because this is actually a different part of the anatomy. This is looking at a different part of the eye, which we shouldn't consider. And then we found other mistakes like this one, a shot noise, and then other artifacts. And then the list just kept going and going and going. And these are all artifacts from large acquisitions that are done in the hospital. And so very quickly, it became clear that we were never going to be able to identify these kinds of extreme cases or outlier cases one by one. So finding rules to remove or avoid evaluating these images, we were never going to be able to scale with the complexity of the problem. And that's actually what we started looking at later, which is basically a problem called out-of-distribution detection. Typically, what you have is a network that's processing an image or a corrupted one, and you have the system, and what you want to avoid is corrupted images being predicted at all. So what a lot of the community in out-of-distribution has looked at is the following setup. Can you somehow have a module or something in before stop the evaluation when you actually shouldn't be processing it? And now that can be a corruption, like a faulty image, but it could also be a different application. So if you have a method that's segmenting or detecting cancer of the lungs, when you run it on a CT scanner looking at the kidneys, well, you shouldn't be making any prediction on there. It should just be saying something of the form, well, this is a different anatomy. My method shouldn't even be applicable here. So this is what we started looking at, and I'll talk about one of the approaches that we came up with. So concretely, the idea is you have a data set, and in our case, our data set actually has no labels. I'm not even going to talk about we want to do classification or detection or segmentation. That's actually completely label-free. And so we're going to have a network, and this network is going to take these images and project them into some latent space, right? We're not talking about classification. We're just using this network as a way to project into some low dimensional space compared to the image. And so when you do this over the data set, you can now think of these points in a high dimensional space. I'm just showing them here in 2 dimensions for the purpose of illustration. But at this point, this embedding can be changed, of course, when you train a network. And when you train the network, basically this cloud of point is going to morph and change in shape. And the question that we thought was, can we figure out a way to change the shape of this cloud in order to, whenever you present an image that's corrupted, when you push it forward into this space, well, that it falls outside of this massive cloud of points. So basically, doing outlier detection in this high dimensional space. So our approach was the following. So again, we have a training data set. It's label free. So I don't know anything about the data except it's just image data. And we have a two-stage process. So on one side, we have a network, which is basically going to take our images and project them into a d-dimensional space. So that's a typical embedding approach. In our case, we're using a ResNet. That's almost a detail. And then we're really going to have a very simple approach, which is a kernel density estimation, which is going to build a probabilistic distribution over this high-dimensional data and provide an R+ space. Now, what does that mean? So in practice, we have our cloud of point, and now we can model any new element as the probability of the observation using the latent representation of an image and all the data. So this cloud using some kernel function, which is basically going to be a parsin window. And so now when you have a new point and you want to measure of this point in the space. So how do we actually train this in order to get something that's doing well? We are just going to actually maximize the log likelihood of the latent vectors in the data set. So really explicitly trying to optimize this function. So we can do this by replacing the density by the kernel density estimation, and we can have this factor. This term at the end is irrelevant from the perspective of the network optimization. So what we end up having is really optimizing this term here. Now there's two problems, as you can imagine, because now our network is being used on one side to define the density itself, P, but also to compute the latent embeddings. So there's a simple approach to avoid this, and that's actually to train by using a copy of the network and updating it at a later stage. So there's many different schemes, and we've tried a few, and in general, this works out pretty well. So what happens when you actually use and train a system like this? We did experiments for both OCT, chest X-ray data sets, and MRI sequences, and compared it to typical approaches in this space. So one of them was a deep one-class classification approach, basically projecting the data and then solving an SVM style one-class classification approach, or then a generative approach called GLOW as a baseline to show how it would compare. These are so-called bidirectional methods or invertible networks. And so in general, it does very well considering corruptions that we manufactured, basically. These are fake corruptions, but a wider range of potential things that could go wrong in imaging. So in general, it does quite well. But perhaps more interestingly is what happens if you try to use a system like this in practice. So here, what I'm showing you is what happens when you take an image, you add noise to it, so you corrupt it more and more, and then you look at the performance of a classification task in this case. So now saying healthy or not healthy for an image, and training that method to do the classification, feeding it images that have increasing amounts of noise to them, and seeing what happens to my performance when you do that. So when you just pass it through the network unimpeded, it's this blue performance. So meaning that as you add noise to your image, unsurprisingly, your network performs poorer and poorer. And so then what these orange and green curves are showing you is what happens if you actually intervened. So in orange, it's showing you that actually if you used this kind of out of distribution detection first, you, to some extent, can't actually detect very marginal amounts of noise, which makes sense. But after a while, you can actually detect them. And that's what this rejection, this other dotted curve is showing you in orange, is the proportion of images that are being now rejected by the out of distribution. So as the noise increases, you're rejecting more and more and more. And after a certain point, you're pretty much rejecting everything, right? And the green is an analogous one with a slightly different threshold. So the system is rejecting as we hope, and able to identify cases it really shouldn't be applying to. Just some qualitative results to show what happens. So in the top left, for instance, we had a real image that's pathological but this is being predicted originally by rejected as a healthy, but our system is rejecting it. So that's really the case we hope for, in the sense that our system shouldn't be making those kinds of false positive mistakes. And on the right, you have more examples that are in fact analogous. In this case, it's quite clear. You have a part of the image that's just shouldn't actually even be allowed to operate on this kind of imaging. So I'm coming towards the end of my talk, and really I want to highlight 2 points here. First is, on one side, what the last 15 years has told us is that estimating surgical instruments and saying where they are in these video sequences is getting really to the point of being close to integrating into practice. But we have this problem of dealing with those tiny outliers. And when we looked at what those are, we opened a whole can of worms, which is dealing with this out of distribution detection problem in generic ways. And there's a tremendous opportunity to do a lot more very interesting research. We're seeing this in the community, both in the medical image community, but more broadly in the computer vision and machine learning community. And so it's been a very exciting developments over the last few years, which I welcome everyone else to join into that more generally. So with this, I thank you very much for your attention. Some people I'd like to thank who were participating in this. And if there's interest, there are some openings at both postdocs and PhD levels in the group. So if you're interested in joining, feel free to email me.
Okay, thanks for Professor Raphael's excellent presentation. So I will pass over to our audience. Do you have any questions? Due to the time limited, we can only ask one question. So you can drop your questions in the Q&A, or you can directly drop your questions in the chat box. Okay, Professor, may I ask you a question? Because during your presentation, you mentioned the safeguarding method. I think you just want to make your model trustworthy, because this is for some clinical and medical things. We do not allow any dangerous. Can you give us more details on the safeguarding?
So here it's really about understanding when these methods can fail. And this is related to what's called data shift. So if you train your method on some data set, and now your test data sets or your test cases are slightly shifted in the statistics of your images and so on, how do you ensure that your method can generalize to them? So on one side, you can try to have robust training methods, and that's fine. But the reality is that if you shift too far, those generalization methods will just simply not hold. And so it's important to understand once you go too far, or that those test cases are just too far from what you're expecting your model to see, how do you even detect them? And so in this sense, there's a lot of safeguarding to do, or data validation or process validation. And I think that's really something that's an exciting area to look into.
Okay, thank you, Professor. This is a very good answer. I think this mechanism of the safeguarding can be applied to many of our authors, because, like, the theme of this conference is the medical image. Okay, thank you.